Looks like everybody's dialed in, so we'll let Frank get going with his talk, which is going to be the best student paper at the ICAPS conference. So this is optimal planning with global numerical state constraints. So thanks, Frank.
Okay, so yeah, my name is Frank, and this is a talk on optimal planning with global numerical state constraints. This is a sort of a rehearsal for the talk that I'll give at ICAPS in a few weeks. And since the time limit for the ICAPS talk is only about 20 minutes, this won't take a full hour. It has been allocated. Okay, I'll start by describing the class of problems that we were interested in solving. So these problems can be thought of as classical planning problems with this additional requirement that certain state constraints have to be satisfied in all of the states or at all times. These constraints can take various forms. They can be systems of equations, they might be PDDL axioms, or they might be something completely different. The important feature is that these constraints are difficult to handle in the existing planning paradigms, but there, however, exist sort of specialized solvers that are efficient in dealing with them. These solvers, however, might not always be the best in dealing with the planning portion of the problem. So what we would like to do is to try to combine the techniques that have been effective in dealing with classical planning problems with these effective constraint solvers. And that's what we did in our work. Okay. I'll start by describing this example domain, and I will be using it throughout my talk to explain some of the concepts. So it's power network reconfiguration. We're given a power network that consists of some number of circuit breakers, some number of loads. There are power lines connecting the network elements, and there are switches that can be either open or closed. The goal of our problem is to reconfigure a network in a certain way. That is, we are given sort of a set of loads that have to be fed at the end of in our goal state. The actions that we are allowed to perform involve opening and closing of the switches. However, we are subject to a number of constraints, as the power lines and the generators all have limited capacities, and we are not allowed to overload them. We are not allowed to feed any of the faulty buses that might be on the network. And in order to make sure that our plans can be executed, we have to make sure that we don't break any physical laws. So these constraints, that is, these models of power flow, can take many forms. The most accurate one is a full AC model. However, there are various simplifications and various relaxations of the problem that make it more easier to solve. And we are using this linearized DC power flow model. We've used that one in our experiments, and I will be using it throughout my talk to illustrate some concepts. An important, crucial feature here is that a single discrete action, that is opening or closing of a switch somewhere, changes the state of the network in a way that is dependent on the state of all the other switches. So that is, before applying an action, we need to make sure that the resulting state won't violate any of the constraints. So now I'll explain our planning formalism a bit, and I will be using our power network reconfiguration problem to illustrate some of the concepts. So we make a distinction between primary and secondary variables. The primary variables are over finite domains, and they function exactly the same way as in classical planning. That is, that are defined as full valuations over the primary variables, and since actions are transitions from one state to another, action effects are defined as assigning new values to some subset of primary variables. In our power network problems, primary variables are states of the switches, and our actions simply involve opening and closing of the switches. Additionally, we have these secondary variables, which do not have to be over finite domains. They can be real numbers. They might include, in our power network problem, these include power flows, phase angles, generation in the generators, consumption in the loads. So an important point here are these switch constraints. So this is how primary and secondary variables interact. Switch constraints are of this form: phi implies gamma, where phi is a formula over primary variables. That is, we call it a trigger, and gamma is some formula over secondary variables. So I will illustrate that with an example. So here's a switch that can be either open or closed. This left-hand side is over primary variables. This says this says switch is open. This is the trigger, and this is the corresponding gamma. That is saying when the switch is open, then the power in the corresponding power line has to be 0. Similarly, we have these constraints associated with the closed switch. That is, when a switch is closed, power flow in the corresponding power line has to be proportional to the difference in phase angles on both sides. Additionally, there's this other constraint saying that when a switch is closed, then either both sides have to be supplied with power, or both sides must not be supplied with power. We call this variable fed. That is the variable that tells us whether a load is supplied with power or not. Okay, the switch constraints are used in 3 ways. First, we invariant switch constraints, and this must be satisfied in all the states. Example include capacity constraints that I talked about earlier, physical laws, and the constraints associated with open and closed switches. Secondly, we have goal constraints, and we say that and the goal is satisfiable if in a certain state, if the union of invariant constraints with the goal constraints is satisfiable. For example, some subset of the loads has to be fed. Finally, we have action preconditions, and that's partially how we determine whether an action is applicable. That is, for an action to be applicable, a union of invariant constraints with the action preconditions has to be satisfiable in a certain state. Now, in a given state, our switch constraints can be either active or inactive. So given this constraint of the form, some trigger implies gamma, if the trigger evaluates to true in a given state, then we say that the constraint is active. From this, we can get a set of active constraints. These active constraints are then passed to the external solver to see whether they are satisfiable or not. We say that the state is valid if the set of active invariant constraints is satisfiable in a given state. Okay, so this can be, I guess, illustrated with an example. So we are given this small power network, which consists of one generator with capacity of 500, and this couple of loads, each with value for load of 200. So we have this initial state in which this switch is open and this switch is closed. This value, this sort of value of this variable over here makes this constraint valid. And this second one makes, active. And this second one makes this one active. If now we take this right-hand side of active constraints and we pass them to the constraint solver, and if we were to do that, we would see that this is satisfiable, therefore this state is valid. So an action that we want to apply involves closing this switch over here. In order to close a switch, we first have a precondition over primary variables, that this switch has to be open, which is true in here. And second, and we also have this secondary precondition, that is difference in the phase angles has to be below some threshold value. Since there's nothing about phase angles in this active set, we say that this one is also satisfied. However, we also have to look at the resulting state. That is, it would make this one open, and no, sorry, yeah, it would make this one closed, and it would make them both closed. This is a bit of a typo. This makes this constraint in here inactive and activates this constraint over here. And if we were to put this in some constraint solver, we would see that this set of constraint is not satisfiable, and therefore this state is invalid. So this is an example of an action that would be applicable in the classical case because preconditions are satisfied, but is not applicable in our setting because the resulting state is not valid. So we wanted to implement optimal planning on our types of problems. For this, we are relying on A-star search. So what we needed is to find some sort of heuristic to guide the search. And for that, we've extended the delete relaxation, and we used it to compute optimal delete relaxed plans. We used the cost of the optimal delete relaxed plans as a heuristic cost estimate to guide our A-star search. Now I'll talk a bit about how we extended the delete relaxation. So for primary variables, our relaxation works exactly the same as in the classical case. However, what we still need to do is figure out which of the constraints are active in our relaxed state. So what we do is we use a value accumulating view of delete relaxation. That is, instead of having a single value associated with each variable gets a set of possible values. Applying an action can possibly add new values to the set of possible values associated with the variable, but applying an action can never remove a value from the set. That is, as we apply more and more actions, the set of possible values on the variable can only grow and cannot shrink. So for some sort of constraint of this form phi implies gamma, if the trigger cannot evaluate to false in a given relaxed state, we say that it's active in this relaxed state. So okay, I think this is best explained through an example. So again, we have this same power network and this same set of constraints. We say that that this one in here again is open and this one is closed. However, this time it's a set instead of a single value. Again, we have two inactive constraints and two active constraints and a bunch of constraints which are always active. This time we will also add a goal, that is we want to have this load over here fed. So we try applying this that is opening this switch over here, and this switch now gets into a superposition of open and closed. That is, no value is removed from a set, but we get this new value which is open. This enables us to make this constraint inactive without making any of the constraints active. However, if we were to plug this this set of active constraints into a constraint solver, we would still see that the goal cannot be satisfied. We apply another action, which is closing this switch over here. This gets this switch into superposition. So again, this set of possible values grows. This enables us to get rid of another constraint, and that gives us this set which is now satisfied. It is important to note here that as we apply more and more actions, the set of active constraints can only shrink. That is, as we apply more actions, we can only discard constraints. We cannot make previously inactive constraints active. Okay, so relaxed planning graph provides us with means of relaxed reachability testing. We use relaxed reachability testing together with the landmark algorithms in order to compute optimal delete relaxed plans, that is H+. The landmark algorithm interacts with our problem only through relaxed reachability testing, and we didn't have to adapt it in any way. However, we found out that computing this optimal delete relaxed plans is very expensive. So what we wanted to do is to get as much from it as possible. The technique that we've devised is useful when the heuristic is computationally expensive but accurate, and states have many successors. That is the case with our power network problem. So our method combines partial expansion A star with preferred actions. Sort of as a side effect of computing the heuristic, we get this set of actions which we consider are preferred actions, and the intuition behind this is that the actual plan is somewhat similar to the optimal delete relaxed plan. This sort of preferred actions has been used in non-optimal planning, but hasn't been used much in optimal planning. So we combine this idea of preferred actions with partial expansion. That is, we initially generate only preferred successors of a state, and sometimes we can reach a goal without having to compute all the other successor states. In our experiments on the power network problems, this results in 42.8% reduction in number of state evaluations. Since most of our time is used on evaluating the heuristic, we get a similar decrease in time required. So okay, so this is a bit different, but initially with the power network experiments, we made the cost of actions constant and equal. And the only objective that we were minimizing is therefore the plan length. However, with the power network problems, a more meaningful objective might be minimizing the area under the curve. And by that I mean, if you plotted load supplied over time, you would get this sort of curves, and you would basically want to maximize this area because you would want to resupply more of the loads as soon as possible rather than leaving portions of the network without power. This is an example of two plans which have equal number of actions, but however this one is better because it resupplies more loads sooner. So the way we formulate this is cost of applying an action is equal to the sum of unsupplied loads in that state. And there has been very little or possibly no work done on optimal planning with state-dependent action costs. We tried to adapt our H+ heuristics to this setting. We've tried to do something with splitting of the actions, but unfortunately we found it too expensive to compute, too inefficient. So optimal planning with state-dependent action costs is still an open problem. Okay, now I'll just finish the talk with a bit of a summary. So what we were interested in can be thought of as classical planning problems with this addition of state constraints. These state constraints can take various forms. They might be systems of equations, they might be PDDL axioms, or they might be something completely different. In order to approach this class of problems, we are integrating techniques that we have been useful in classical planning with an external constraint solver. We are basically using the methods that were good at for classical planning, which is like heuristic search. We've extended the lead relaxation. That our heuristic was very expensive to compute, so we tried to figure out a way of getting as much as possible from an expensive heuristic. And for that purpose, we've developed this preferred actions in partial expansion A star. And we've tried to do something with optimal planning with state-dependent action costs, but we found out that that what we did wasn't very efficient, so it's still an open problem. Okay.
Can you get the slides up?
Okay.
There's a question about the state-dependent action cost.
Yeah. Yes.
Could you, I mean, I don't know, I haven't really thought about this, but could you create an action with just additional preconditions to represent the state and then have that cost applied for that specific action?
Yeah, but that would get you many copies of a single action.
Yeah. So.
That will get you 2 to the power of, like, if you have sort of.
But so I mean, the question really is, I mean, is the cost dependent on those exponential many states, or is it really only dependent on a subset of variables or a subset of key state variables that is really sort of determining the cost?
Well, it's the cost of an action is, say, the sum of the loads that were unsupplied, and like there are many ways of getting. Like in a power network, there are many ways of getting different costs. So that would just give you many copies of an action. So like I don't think that's possible.
Hi, can you all hear us? I have a question from Newcastle, if you can hear us. Can you hear us?
Yes.
Okay. So my question was, first of all, is your test data coming from a real power company? And if so, I'm assuming this is at the kind of suburban level of network. Is that correct?
Yes, I don't feel that.
Why don't you repeat the question?
Okay, so the question is, are you working with a real power company and are you testing on real data? And if so, I guess I'm curious about the size of the network. Is it a suburban size network? How many arcs are in the network, etc.
Well, the network that we used in the experiments is a real power network, right?
I can answer that. If what you've used is the semi-rural network,
that's the one that was used in the that's the one that we've used in the experiments.
This is a network that was given to us a long time ago by a French company, EDF, as representative of the complexity of networks that are used in France in a semi-rural environment.
So I do have one follow-up question then. So I wondered if I've done some work on this problem on networks that come from the Newcastle area with a local power company, and they were very concerned about the DC model. They were not happy with the DC model, and they felt that in the failure situations that might lead you to reconfigure switches, that they only would trust the AC model. And I wondered if you'd done any validation and encountered yourself any problem with this network in failure situations with the DC model.
So, this sort of approach can work with the other models of the power network other than just the linearized DC model, as I've said. I mean, we can sort of use more complicated equations.
So I guess the reply is that we can do that. We haven't done so, and that's part of related work. I mean, you should see this research, this particular research, as still, trying to bring planning technology to a stage that it can cope with real-world problems. But at the moment, I don't think this would, scale to something of the size that you're having in mind, right? So this is like really the first step at the moment. We also have an approach that's using MIP or NLP or a quadratic programming with some relaxation of power flows, and that's working better than this. Also, this is solving a much harder, potentially harder problem, because you don't have to specify the number of time steps that you're using in your plan, which you would have to do with a MIP or NLP or something like this.
Okay.
Yeah, thanks very much. I think it will be great to see some kind of a more exact or optimizing approach actually succeed. That would be really great. I mean, the only approaches I've seen and that I've used myself have been genetic algorithm, evolutionary algorithm type approaches, because I agree that for the AC power flow and other more complex models, it's very hard to get exact solvers to do anything. So I wish you every success in making this work. Thank you.
Who is this, by the way, Sylvie?
Oh, it's Natasha. Hi, Sylvie, it's Natasha.
All right.
This is Carlton from ERL. Can you hear me?
Yep.
So I have a question for you, Frank. Thanks for the talk. Why would you say that this is a planning problem rather than a scheduling problem?
Well, I don't know, we modeled it this way.
You don't know what the actions are.
Sylvie, you're helping. That's not fair.
Oh, okay, sorry. It was a trick question. I didn't realize.
I know the answer. Come on.
Yeah. So what?
wait, so what was the answer? I didn't quite hear it.
Why is this planning rather than scheduling a problem? I don't know. It's just formulated that way. You have actions with preconditions and so on, and you try to come up with a plan rather than a schedule. Yeah. Yeah.
So, Carlton, what was your answer?
Yeah.
What was that?
So what's your answer? Yeah.
You're asking me what my answer was?
Yeah.
My answer would be, in the example that you've shown, you need to open a switch before you can close another switch. And so it would be hard to know that ahead of time in the scheduling kind of context.
So you're saying it's just because there's sequential constraints that you need to enact a plan rather than a schedule?
I mean, the reason why it's a planning problem is that the actions are not known in advance. Scheduling is really about deciding when certain actions are going to be performed in order to minimize to optimize some, I don't know, some cost function once you've already decided what are the actions and the constraints between them, right? Here we're deciding what the actions are, so it's a planning.
But Sylvie, as a scheduler, could argue in the optimal case that was discussed at the end of the talk that it's just a series of closing actions, and so you just need to decide when the closings occur.
Well, you also have to decide the openings.
Yeah.
Well, so that is the generalization, which I think is key to making it a planning problem.
I don't know.
Yeah, well, I mean, this is like the level 1 versus level n plan, right, in your terminology. If you consider only level 1 plans, yeah, then you need to schedule.
But you still have to still a sequencing point.
Yeah,
All
but
right,
I mean,
okay, that's what he said.
scheduling can sequence constraints. Precedent constraint is nothing.
All right, okay. I see what it's like. So,
All right.
Can you hear us?
Yeah.
Hello, Frank. So I was wondering, have you considered a scenario in which you can substitute parts of your configuration with smaller networks, let's say individual switches with networks, with entire networks?
So like take a network and replace one portion of the network with a
because right now when the switch is open, then you actually cut part of your power flow, yeah. And if you replace the switch with, let's say, parallel switch, you would be able to distribute somehow the power flow, and then you would be able to build plans in which you maintain most probably more optimal consumption. I don't know, distribution of the loads. It's just an idea. I don't know what exactly you may gain, but in order to preserve some of the power flow through individual switches, you may replace them by parallel switches, for example. Have you considered this?
Like in order to preserve flow through some of the switches, could you please repeat that again?
Yeah, so you can replace the individual switch with a parallel switch.
No, we haven't really considered that. But like I think that would change the problem considerably.
Okay.
Yeah.
Yeah, I have a question.
Yeah. Okay.
So if I understand, you're calling an external solver.
Yes.
For each state. Right?
Yes.
Each time you want to run it.
Yes.
Are you taking advantage of the fact that you're solving the same set of?
Yes, I am. So
you're not solving it from scratch each time.
yeah, no, I'm really like the solver can sort of remember the previous solution and can start close to the solution. So yeah, I am reusing the solver. I mean, I am reusing the model with the solver. Yeah. Yep.
Some questions you might be asked. So
Yep.
try them now. So what is the difference? What is the essential difference between what you're doing and what Piacentini et al. Did last year?
I think yeah. So I think they don't really consider I think that they've sort of outsourced this like opening and closing of the switches to the constraint solver, because like I think they're using some sort of specialized for solving power problems. Yeah.
And what's the difference with planning modulo theory?
Yeah, I'll look into that.
You need to prepare this, because this will come.
Yeah, I know that.
I thought that was your homework from last night.
Okay.
All right. Thanks a lot, Frank. Does anybody else have any questions? Everybody good? All right, Frank. Thanks a lot. Thanks again.
Thank you.
Have fun.
We don't have
ICAPS.
seminar. Yeah, good luck at ICAPS.
Yeah.
Next seminar is June 13th. It's going to be Andreas.